So we had just said that you can move from any point on a plane to any other point on a plane by, using two non-collinear vectors. And the easiest example to use is two perpendicular vectors in two dimensions. So remember, this is a plane. This is the plane of your desk, the XY plane. And if you can move north, south, east, west, you can get to anywhere on your desk. Now, the part of this that's really, that I don't think is very hard to understand. You've been using that idea for, as long as grade 9 and before. The part of this that gets weird is the part that actually I and j don't have to be perpendicular, and this still works. So we can make I and j different values, and this should still work. So quickly to demonstrate one more time, you can see that if I use some amount of j and some amount of I, right, I can get to my destination point, right? I'm just trying to demonstrate that here, where you're using, some amount of these two vectors to get from one point on the plane to any other point. Now again, imagine we change I, right, so that instead of 1, 0, it's now 1, 1. So it's pointing off in this different direction. And then let's make j something, I don't know, -2 and 7. Right? So now I and j are pointing off in these completely, weird directions. And yet, if I think of my origin as point B and my destination as point A, there is still a way, right, for me to, we'll make this even stranger. Let's make it 3, 1. There's still a way for me to stretch this out, right, and still get to wherever I need to get to. And of course, I might not be able to get it demonstrating. Right? There's still a way that you could always sort of line this up, right, with the correct number that you would need. Now, again, I got to make this a bit more precise. Okay, and there you go, right? Now I've got two different vectors, I and j, randomly picked, and yet I can still use some combination of I and j to get from one point on the plane to any other point on the plane. And this is a difficult thing to understand. We get this when they're perpendicular. But as long as they are not collinear, this works for any pair of vectors, right? Let's make I, again, a random one. Random between -5, 5. Random between -5 and 5. Right? You can still make I a totally random vector, and some combination of these two is still going to enable me to get from A to B. Now, the kind I have here is going to make this particularly difficult because I have to send it this way and then come back up. I need to send it like way down into the negative and then bring it back up into the positive. But even this like really, really weird pairing of vectors still works, right, as a way of getting from A to B. And this is quite bizarre, right? Now, of course, you would realize that, picking I and j to be perpendicular makes the most sense because it's the easiest way to move around in two dimensions. But the point I'm trying to provide you with here is that the concept of a plane is equal to a point plus t times m1 plus, s times m2, and that's going to be that will get you from any point on the plane to any other point on the plane. And even if the two vectors are bizarre like the two I've picked here, it still works. And this is the reason why even to, vectors that don't seem like good candidates for the basics of a plane, what we call the basis vectors of the plane, don't seem like they'll work, they still do. So as long as you have any two non-collinear vectors and a point, you can create a unique plane. Okay, that will specify exactly one plane, and that is why our equation looks the way that it does, right? Why does it look like this? The plane is equal to a point plus a certain amount of parameter s times one direction vector, and then parameter t times the other direction vector. That will create a plane. Now, of course, this can be changed into a parametric form. It's the same thing as it was for a line, just recalling that a line would have stopped here, right? XO, YO, ZO plus T, A1, A2, A3. So A1, A2, A3 is the direction vector, S is the parameter, and XO, YO, ZO is a point on the line. To change that line into a plane, we simply add another direction vector. This one is vector B, and another parameter. You can still isolate the parameters one at a time, x, y, z, and they still create, they're still the parametric equations of a plane. So again, x is the first coordinate, so xo, s times a1, t times b1, and that's your equation for x. You simply do the same things, and that creates your equation for y and z. So now you know how to create the equation of a plane, and you can change that equation from vector form into parametric form. Remember, what does the equation of a plane do? It is a roadmap, a way of figuring out what points also lie on that plane. Any point on that plane could be arrived at by starting at your original point, adding some amount of vector 1 and some amount of vector 2. Let's try this now, and we'll actually see about just doing some of the examples and do some of the work here while we've got a chance. So some of the work. So let's start with question 1. The vector and parametric equations for the plane that contain 3 points. Okay, so first of all, 3 points equals specifies a particular plane. So we definitely, this is going to work. There's no, the 3 points here, as long as they're not in a straight line, will work. So let's see how you would do this. Again, some of this is in common to the way we would have done it with a line. So let's see, in order to create a plane, remember, is a point plus t times m1 plus s times m2. We need 2 parameters, and we need a point. So the point is easy enough to get. The point, you just take any of those points that you found. So pi for our plane is going to be specified by, okay, let's do point B, 524 plus t times some vector plus s times some vector. And of course, t and s elements of real numbers, just to remind us. How do you think I'm going to get a vector that's on the plane? I need to get 2 vectors that are on the plane, t and s. Let's go into GeoGebra for a second, quickly draw this one. So if I go back into 3D, okay, delete everything I have here, and I'm just going to draw these 3 points. So we have 1, 1, 1, 5, 2, 4, 1, 1, 1, b is equal to 5, 2, 4, and c is equal to 3, 2, 0. Okay, now the plane, right, needs to contain those 3 points. In order to get the equation, we need 2 vectors and a point. We've already chosen a point, that's point B, so let's get a vector. An easy vector to get would be the vector that joins B to C. There's one of the vectors that has to be on the plane, right? Another vector we could use is vector B to A. Vector B to A. Now we have a second vector that's on the plane. If I tell GeoGebra, plane, okay, the point B, the vector U, the vector V, it can create the plane that contains those 3 points, no problem. So this is a very, very easy exercise to create the equation of a plane given 3 points. All you need to do is, let's make a vector here from B to C, and here we'll make a vector from B to A. And there you go. Now you have this, we just found out the equation of this plane. It's 524 plus t bc plus s ba. Again, just to give a quick demonstration of how you do this, remember you just do destination minus origin, and you can easily create as many vectors as you need from these 3 points. You can do AB, you can do AC, you can do BC, BA, whatever. The important thing here is that BC and BA cannot be collinear. And if they are collinear, then the question that we were asked is impossible. You can't make a plane that contains those points. Or, sorry, more accurately, you could create many planes. There's not just one specific answer that you need. So you can create a plane by knowing a point and two vectors. And it's easy to draw those two vectors. Just join two of the other points that you know happen to be on the plane. I chose to start with BC and BA, but you could have easily done CB, you could have done CA, you could have done AC, you could have done whatever two you want, as long as you didn't do CB and BC, because those two point in the same direction. They don't, those two would be collinear. You have to choose two that are not collinear. So make sure that each point is involved somehow in your creation of the vector. So we can answer this question easily. We just need to go, all we need to do is just write down the vector BC and the vector BA. So vector, to get from B to C, I would need to go -2 in the X, 0 in the Y, and -4 in the Z. To get from B to A, I would need to go -4 in the X, -1, and then -3. And there's that would work. Now again, this is not the only answer. There will be many answers that describe this, but all of the answers will describe the same plane. There is still only one plane that actually works here. To go to the second part of the questions here, so the next point, it says determine the vector and parametric equations of a plane containing the line such and such and the point such and such. Okay, so let's try this one. So determine this time I'm going to do the parametric equations because I skipped those last time. Okay, so this time we need the vector and parametric equations of the plane that contains this line. So a line and a point. So again, think to yourself, what do I need for a plane? I need a point. Well, let's pick the point that's on the line. If the line is on the plane, then whatever's on the line is also on the plane, right? We need a vector. Well, one good vector would be the direction vector of the line, right? Whatever way the line is going, if the plane if the line is on the plane, then the plane has to be going in that direction. It has to be parallel to that line as well. We now need a third vector, right? And of course, we haven't used this point 1, 1, 1 yet. So let's use the point 1, 1, 1 minus -3, 4, 6. And what that will do is it will create a third vector that joins this point to our line. And that vector at the end here would be 4, 1 take away 4 is -3, and 1 take away 6 is -5, right? So we now have a point, a vector, and a vector, and this is going to specify the equation. So parametrically, we start with x is equal to -3 plus 5t plus 4s. I'm going to say this one goes with t, and this one goes with s. It doesn't matter which ones you pick whatever you want. Y is equal to, okay, the y coordinate is 4, 2t, and minus 3s, and the z coordinate starts at a 6. We take away 3t, and we take away 5s, and there you go. This is the equation that contains that line and that point, okay? Again, this work is just meant to get us introduced to the idea of creating an equation. This, of course, is not very difficult once you get the hang of what am I looking for and what do I fill in, right? So let me just quickly check that we did this one right. So I'm going to go, it has to contain the point 1, 1, 1. It has to have the line -3, 4, 6. So we're going to change B to -3, 4, 6. And it has to contain the direction vector 5, 2, -3. M equals 5, 2, -3. Now if we make a line that contains point B and this direction vector, that line is over here. I need a plane that now contains this line and my point A. And you can see I need to do it point first and then the line is a criteria. And then it has, I know this doesn't look right, but it is actually right. This line you can see here, if I just sort of zoom it out a bit, it's a bit easier to see, right? That line lies on that plane. Okay, now again, the equation that GeoGebra made, it makes scalar equations, so we'll talk about that tomorrow, and we can't really do much with that right now. But the idea here is just to follow what we talked about before. You create the vector for each one, and then the plane. So I'm just going to check our work by doing the point with the two vectors.